Let's get another model here, um, just to break it up a little bit. Newton's law of cooling. What happens when you take a nice pie out of the oven? Besides eating it, it cools down. But the question is, how fast? The answer, it cools down exponentially. So this is just laws of physics. To what temperature does the pie degrees to? The answer is room temperature. Now, this is a very important situation. In engineering, this is critical. You got parts heating up, and heat is usually not a good thing for parts. So we're trying to cool them down. The question, how fast? And again, one thing in this particular pie scenario, we're making some massive assumptions. Obviously, heat transfers. That's where we have a heater in a house, and they're trying to warm it back up, trying to bring room temperature back up. But a pie is, some objects are so small relative to room temperature, right? A large room. So we're assuming, of course, the room is large. If all of a sudden we take this pie, just come out of the oven, put it in a box, then all of a sudden that's not going to apply. And that's why sometimes when we ship something like cool or something, we put it inside a little box, and then all of a sudden the temperature of this thing is hard to change because it's sealed. Especially when you have maybe styrofoam or something that does not transfer the outside temp into the box to maintain the heat, right? That's the whole point. So it turns out that what do we need to figure out the temperature of an object once you expose it to other temperatures, like room temperature? So let T naught, little zero here, equal the initial temperature of the object. Let Ts be the surrounding air temperature, so Ts for surrounding. Let K is a continuous rate of cooling of the object, which varies according to the physics of the object. So a piece of metal is different from a pie, which is different from some other object. So the temperature of the object, it's in some time units, whatever they happen to be. So the temperature of the object some time later is given by the following formula, which says, look, it's the difference between the original temperature of the object minus the room temperature or surrounding temperature. So this goes, the difference of these two is being multiplied by E to, again, that cooling constant times T, plus the room temperature. Okay, and that's the object. So you can notice, again, this is a vertical stretch and vertical increment. And here we have some kind of a stretch as well. It's going to be. So let's look at a particular example. Room is 50 degrees Fahrenheit. Okay, 50 degrees room is a room, so surrounding is going to be 50 degrees, and this is in degrees Fahrenheit. The drink is heated in the microwave to 105 degrees Fahrenheit. Okay, so now this is going to be the original object of the object is 105 degrees Fahrenheit. After 2 minutes, the drink temperature is 94 degrees. Okay, so this is in minutes, so 2 minutes later, then it's now at 94 degrees, so which means that T at 2 is 94 degrees, again, Fahrenheit. I'm assuming it didn't say. What is the value of K? The continuous rate of cooling for the drink. Okay, so I'm just after the K part. So what I do have is, if I follow that formula, I got the output is 94. The difference is going to be 105 minus 50. Again, the difference between the object and the room temperature, E, K, I don't know. And this happens 2 minutes later. And again, surrounding room temperature is the 50 degrees. So I need to solve that equation to figure out what the K is. So I'm going to subtract 50 from both sides. Again, I need to bring this exponent down, but I need to wipe out everything that's around it. So I'm going to subtract 50 from both sides. So I'm also going to figure this out. So I subtract those two, and what do I get? It looks like 55. Yep, I can see that's 55. Great. Here, what am I getting here? 94 minus 50. Oh gosh, oh gosh. I don't want to. Oh yeah, 44. Okay, okay. Momentary mind melt here. Divide both sides now by 55. So I'm continuing to solve. And now I have the variable is k, just sitting up there. That means I'm going to have to take the natural log of both sides to bring that down. And I could take any log, but it might as well make it natural log since the base here is e. It makes most sense to do that. So now these are inverse functions. I get 2k when I do that. So again, inverses is the input. E takes this input somewhere and natural log brings it right back. That's why I get 2k. So they just undo each other. And now divide by 2. And bingo, I have k. And this is the exact amount. This is the exact value of k. Not an approximation, exactly that. Okay, I'm gonna leave it that way. Because I need to use it in a second. What will be the drink temperature after 20 minutes? Okay, after 20 minutes, what's gonna happen? Okay, now I'm gonna make sure that my original one was at 2 minutes. Yes, so T is in minutes. I need to look about the information, how I created this. So T is in minutes, 20 minutes, I'm happy. So now what I need to figure out is 20, T of 20. 20 minutes later, what is the drink? So I cleaned this up quite a bit. Up here, look over here, E55, E. Then we have after 20 minutes, so 20, and now K, of course, is not K anymore. This is K. So I'm going to write down what K is, which is pretty big, right? But that's why sometimes physics formulas are so big. You want to write exact values sometimes and then later approximate them. And this is plus the 50. So here's the original plus 50. That's a room temperature. Also notice that if you make this or this variable at 0 time, all of a sudden you have 0 times this amount. This will become 0. E to the 0th power is 1. 55 plus 50 was the original amount of the temperature. So really, the original amount of the temperature is broken up by having the room temperature plus the difference between the object and room temperature right here. So keep that in mind that if you add these two numbers, you'll get the original amount of the object. Okay, great. But I mean, I just put everything in here. It's not much to do except just calculate. So I'm gonna just put it in one shot. So notice I'm not breaking anything up. You should get used to that. That's what I'm kind of doing is so you get used to just doing this. There's no point in breaking the 71 down. You have enough knowledge of algebra. We're not testing this now. We just want to get to the bottom of this. So one thing I'll notice that 20 times a half is 10. So I'm going to just enter 10 here. And if I could reduce a 44 and the 55, oh yeah, I can. This is a factor of 11. This is a factor of 11. Oh, that's cute. So divide this by 11, divide this by 11. So that's going to be 4 divided by 5. Oh, nice insight. Close it up and plus 50. And what do I get? That. And that should be, what am I just get? Okay, I'm going to approximate this. This is degrees Fahrenheit. So this is the temperature of the object 20 minutes later, and you notice that it is just now above room temperature. Right? Why? Because it's decreasing, but it's decreasing exponentially. All right, that's fine. Let's do another one. All right, when will the drink cool down to 70 degrees? Okay, so we'll look up. So now I'm going to get again use this formula one more time, but this time I'm asking when will the drink, and then remember T is in minutes. Okay. But I wanted to cool down 70 degrees, so the output now is 70. I'm using this formula again, but this time the variable is time. So T, and then times this amount. And now I realize this could be expressed as 4/5, so I'm going to clean that up, 4/5. I guess I could bring that up too and clean this up too, but I'm just not going to right now. Leave it that way for now. And now I need to solve this. Oh no, plus 50. There we go. Now I need to solve that. Which again, I have my exponent, so this is an exponential. So I'm going to start by subtracting 50 from both sides. Great. And I get 20. Oh, okay. Right here, be careful. So again, notice if you're nice and neat, if you make a mistake, you can sort of capture. So before I was about to write down, look here, and then look back up, make sure it looked clean, but then I realized I was missing something. So I get the following. And I should clean this up a little bit too. T halves times natural log of 4/5. Let's just clean this up a little bit. Okay, I like that better. Now I need to divide both sides by 55. Oh, I see why I didn't want to do that before. Okay, never mind. I'll just leave it like this. I see my next move. And what is my next move? I need to take the natural log of both sides to release this in the exponent, and I think it just will be nicer if these two are apart. So I'll take natural log of E. So if you're going to do any higher mathematics, you have to get used to writing a lot. Okay, so do you notice how I'm writing things nice and neat? I'm not interfering with results. I'm writing over again. This is the only way you can do higher mathematics, because you write a lot trying to go step by step, and there's multi-step processes. So if you try to keep things too brief, then things break down. Okay, I have this, and now this is a linear equation. This is a constant, that's a constant, that's the only variable. Divide by that whole constant, which is half of natural log of 4/5. And there you go. I guess I could reduce that down to it's okay. Took that natural log of 4/5, divide by parentheses 0.5 times natural log of 4 divided by 5. Close it again. Yep, I'm happy. Okay. So 9.06 back in 7. And now what is the time unit? Oh, it's in minutes. So this is minutes. And that's T, approximately. So it will take about 9.067 minutes to cool down to 70 degrees. And that feels good.